Hello, everyone, and welcome. I'm Joanne Emery. I lead the IHS Infinetics webinar group, and I do want to thank you all for joining us. Our webinar title is the Metro 100 Gig Coherent Evolution, and our panel today is going to be looking at drivers and multiple technologies for Metro 100 Gig. We've got some use cases we're going to look at, and we're going to talk about different approaches to solving cost and density challenges in this market. Our webinar today is co-presented by IHS and our partners Cisco Systems, Coriant, and Oclaro. Just before we start, I'm going to quickly review some features available for you on the console and also talk about how you can participate on the webinar. First thing, the console that you're viewing can be customized, so you can move or resize any of the windows that we've preloaded. We have your presentation slides positioned right in your center window, and we do recommend you maximize that window for better viewing of your slides. And you can do that simply by clicking the green button at the top right corner of the window. You can also resize this, or you can resize any window just by grabbing the bottom right corner and dragging. Also, you should see a row of buttons that are running along the bottom of your screen. All of these widgets contain information and more features for you, so I encourage you to check them out during the session. I'm going to call out two of these buttons for you. First, our resource list. That's the button that looks like a little file folder, and it's where you can find the downloadable version of our deck from the session. In addition to the slides, we have a companion report from analyst Michael Howard focused on 100 gig in the Metro. We also have access links and other materials, a lot of background on today's topic. So I do encourage everyone to visit the resource list area and download those reference materials. Another area I'm going to mention is our help button. We really hope you don't need this, but if you have any technical difficulty, you can click here. That's the button with the question mark icon way over on the far right side. This is where you can get answers to any common technical issues right there. And now just some ways you can participate. We have a Twitter feed that's running on your console. You're going to see tweets loading during the session, so you can view and you can post right from the webinar. We are using a hashtag 100G today. Last item I'm going to mention, we will have a dedicated Q&A session directly after the presentation. So submit questions or you can submit comments anytime during the session. Just use that Q&A box on the left side of your screen. We're going to be monitoring your input all through the webinar, and we'll get to as many questions as possible. So please get your questions in early. Any questions we can't get to on the webinar, our panel is going to follow up with you directly. And so that's it for the details here. Now I want to introduce Michael Howard, who will be leading the session. Michael is Senior Research Director at IHS. He drives the Carrier Networks coverage area, and I'm going to pass the controls over to Michael. So Michael?
Thanks, Joanne, and I'm excited to be here today with this panel of experts. First, I'd like to say that I've been involved with optical networking since 2001 when I created our original optical network hardware service. Around 2009, Andrew Schmidt took that over when we hired him. I've been his backup for the last 5 or 6 years, and he's now departed from our IHS ranks. So what's been exciting to me is, although I've been backing up the service, there's a lot of new technologies that it's amazing. When I look back 5 or 6 years ago, 100 gig was kind of out in the future somewhere. And now we have multiple ways of deploying 100 gig, new technologies coming along, and it's not just 100 gig, it goes up and beyond 100 gig. So I'm excited about the webinar. I've learned a lot already, and I hope you learn a lot today as well. So welcome aboard. First, I'd like to introduce Ron Johnson. He's the Director of Architecture and Product Management at Cisco. Ron?
Thank you, Michael. I've been in transport now for a little over 20 years, and I'm excited to, as you said, the pace of innovation is really amazing. And to have started my career with OC48 being the state of the art on a piece of fiber to now talking about tens of terabits on a fiber is it's really amazing how far it's come in such a little amount of time. But I'm excited to be here. Thank you.
Thanks, Ron. And of course, there's cost trade-offs everywhere. Paul Momdahan is the Director of Optical Solution Marketing at Coriant. Paul?
Hi, so this is Paul Montahan. I've been working in the metro optical space for about 10 years now in a number of roles, including technical sales, working closely with operators, doing a lot of network designs, in product management, and now in solution marketing at TAL Labs and now at Corient.
Great, thanks. Welcome aboard. And Robert Blum is the Director of Strategic Marketing at Oclaro. Robert?
Yeah, thanks. Yeah, thanks, Michael. Yeah, obviously I've been in this industry also for quite a long time, 15 to 20 years, and yeah, this is a particularly exciting time with this tremendous growth in bandwidth, and I look forward to talking about the trends and challenges we're seeing. Michael?
Great, thanks. Welcome aboard. So let's get started. I'm first going to, we're trying to hit 45 minutes with the content. Be sure to ask questions along the way. We may answer them along the way, but more likely we'll answer them at the end of our presentations. So you will get these slides. You can download them. So part of our mission here is to talk first about the market trends, briefly set up what's happening, look at problems and challenges, and then, interestingly, looking at what are the new options and solutions available now. And how are service providers deploying these applications, or how do they intend to deploy these new options? We'll take a few minutes at the end for sponsor approaches. I'll run through some conclusions quickly, and we'll be on to audience Q&A. So first, I'd like to ask Robert, how do you view 100 gig and what's going on in optical transport in the different parts of the network?
Yeah, thanks. Yeah, so the diagram on the right is basically my view of the fiber optic world. I've grouped it in three areas: fiber access, data centers at the right, and co-routing and transport. And I'm also showing trends that we're seeing. For example, in wireless, we're seeing 10, 12 gig deployed today, but also people starting to look at 25G as they're thinking about moving beyond 4G LTE in the future. Similarly, in the data centers, we see 40 gig optics being deployed today in the switches as they aggregate the 10 gig lines from the servers, but we see obviously a big momentum going to 100 gig as data centers are moving to 25 gig at the server over the next year. So, but what I really want to focus on is on the very right. If you look at the DWDM core, 100G has been really deployed for many years. It's a very mature technology, and people are now starting to look at 400G, what they can do in the next few years. So that's a very mature technology, but to deal with all the bandwidth that's generated further downstream at the users, at the enterprises, in the data centers, there's a lot of pressure now for the metro to upgrade to 100G as well. And that's really what we're going to be talking about in the future slides. But what we also see is that the requirements for 100G in the metro are somewhat different from the requirements in the DWDM long-haul network. So we'll talk about how what we can do there and how we get to more flexible solutions that can scale to the requirements of the metro. Michael?
Yeah, and meet cost trade-offs in different parts of the metro. But first, there's the famous saying, a rose is a rose is a rose. Bandwidth is bandwidth is bandwidth? Well, maybe not. Ron, what do you say about the traffic growth?
Yeah, I think it's really interesting to look at some of the applications that are driving a lot of this growth. And the major one is really video. And video is coming in multiple different flavors. The kind of traditional broadcast video, the likes of YouTube, with personal videos, and then streaming over the top stuff that's being driven by the likes of Netflix and Amazon. It's certainly the big portion of the bandwidth, but we're also seeing things like data centers moving into the cloud environment and having a larger separation between branch offices and their data that they need to access. And then kind of an up-and-coming thing is things like machine to machine, and the likes of IoT, having sensor capabilities that may have a lot of or very, very, very little bandwidth, but there's potentially so many of them that that it adds up, and it certainly impacts the transaction scale of the network. So a lot of exciting things that are happening, and an indication that there's really no obvious end in sight to this bandwidth growth.
And this points to the need for different types of technologies in different parts of the network. So we're going to look a little deeper now into what are the problems and challenges. And so, Paul, how do you see the challenges?
Okay, so we're seeing tremendous growth in metro bandwidth and traffic, and this is really primarily being driven by three key applications. The first application is internet video or over-the-top video, and this is really driving significant growth in terms of the IP traffic that stays within the metro from the network to users and between users, and this is forecast to triple between 2013 and 2018. So that's the first one, is video. The second one is cloud, and in particular enterprise cloud, with workloads moving increasingly to the cloud, and in particular moving to public cloud, which is growing at a 44% CAGR. And then underlying these two trends is data center interconnect, which is the east-west traffic flows between data centers to support this video and cloud, and that's growing by a factor of 4 in the same time period. Okay, so that's kind of the good news. So we're seeing tremendous traffic growth. The issue is this: 10 gig has really been the workhorse of the metro. It's driven very nice cost reductions year on year as volumes have increased, and as we've moved to pluggable technologies, first XFPs and now SFP pluses. The issue is that 10 gig DWDM is now a very mature technology, and any further cost reductions are really going to be quite incremental. So these cost reductions aren't going to be able to keep pace with the tremendous growth that we're seeing in terms of the traffic. So that's the first problem. The second problem is there's always been this kind of view that in the metro, fiber's available and it's not expensive, so you can throw fiber at the problem. Spectral efficiency isn't that important. But as we see these huge increases in traffic, if we try and throw fiber at the problem, it has both a capex cost because we have to light that fiber with ROADM degrees, but it also has an operational cost. You can have lots of parallel fibers and parallel lambdas, but that becomes operationally expensive to manage. And then the third issue is power consumption and footprint. In terms of getting more bits per second per rack unit and more bits per second per watt, we're kind of getting close to the limitations of where we can go with 10 gig, especially as we've moved now to SFP plus. So those are really the problems that we're looking for 100 gig to solve for us.
Great, thanks, Paul. And to solve these problems, we depend on components, and it's not straightforward of how we get from it requires innovation to keep moving up the bandwidth scale. So what are the problems you see, Robert?
Yes, on this slide, I wanted to talk a little bit about what's being deployed today, right? I mean, most 100 gig DWDM shipments are really in the form of line cards today. And what you need to do for that, from the optics perspective, you need to have a tunable laser on the transmit side. You go through a lithium niobate modulator to modulate the light. And these are pretty complicated components. I mean, you have two pairs of nested Mach senders, or the bias control, the drivers for the modulator. And then on the receive side, you have another narrow linewidth tunable laser to act as the local oscillator, and the coherent receiver or intradiode receiver, and the coherent DSP. And so that's a lot of optics, 4 different components with a lot of discrete electronics. And to make the point here, I'm showing you here what an actual module would look like, a line card or module in this case, this is a little bit of an older picture or older design, but fundamentally, if you look at what's shipping today, that's it will look pretty much like that, and so you see all the complex electronics, you see all the fiber routing, all the heat sinking. So this is clearly very mature in a way, but it's also not really scalable. If you want to do multiples of 100G. It doesn't scale. You have to have multiple designs, and really for the metro, we need to do something different, something that can scale beyond what you see here, and we're going to talk about that in the next slide.
So Robert pointed out here that there's lots of different points in the trail of a pathway for a light wave and for traffic. So, Ron, what's the state of the art of high-speed technology?
Yeah, I mean, if we look at the most recent generation of switching, packet switching or OTN switching chips and packet routing chips, these chips are really talking 25 gig SerDes across the line card, and they talk to optics through the back side of the optics, electrical side of the optics, and that gets mapped to some number of essentially wavelengths inside of the gray optics. It could be, in all of these cases, whether we're talking about SR10, SR4, CWDM4, LR4, or LR4 Lite or LR4, it's some number of wavelengths or fibers that are used to do that interconnect. Then on the other side, as we transition to fiber or to a transmission system, we have 25 gig electrical lanes again talking to the latest DSP technology. That DSP talks analog over multiple lanes to an optic, and that optic is packaged today in a CFP2. So it's a very aggressive packaging compared to what Robert showed in the previous slide, and then it gets put onto a fiber, and all of this today generally is thought of to grow simultaneously or thought of to grow together. And what we'd like to refer back to on this later is how is this going to change, in the very near term, and how are we going to allow these technologies to mature at their own rates and take advantage of them as quickly as possible?
Well, we'll find out the answer to that in a few minutes. We're going to now look at what are the new options and solutions to solve these problems that we just talked about. And so I'm going to ask Paul to speak first to this. What are the options for the evolving metro, 100 gig and beyond?
Yep, so really broadly speaking, there are three key directions we can go in to take the current state-of-the-art 100 gig based on coherent pole-mux QPSK and evolve that to drive down the cost per bit and to improve the footprint and the power consumption. So the first option is really to move to higher modulation, so to get more bits per symbol and more bits per second at a lower incremental increase in hardware cost. And we can do that in the short term with 16 QAM and 8 QAM, and then longer term, we're looking at 32 QAM, 64 QAM, and even 128 QAM. So that's the first option. The second option is not to change the modulation, to stick with exactly the same modulation, so coherent pole-mux QPSK, and really just drive to smaller pluggables. So from CFP to CFP2 to CFP4 to QSFP28, and maybe in the future to something smaller, closer to an SFP+. So that's a second direction we can take. And then the third direction is to get rid of the coherent, which is an expensive part of the solution, and look at non-coherent single or dual channel technologies based on modulation such as PAM4 and DNT. So those are the three key directions we can go. But it's worth pointing out that they're not mutually exclusive, particularly as the smaller pluggables can also apply to the non-coherent and to the higher modulation. So those are the options. Next, let's take a look at what the relative strengths and weaknesses of each of these options are. So if we look at the non-coherent 100 gig, this is available a little bit later, and the reach is going to be limited, maybe in the 40 to 80 kilometer range. But it offers the potential for the lowest possible cost per bit. So that's really the strength of the non-coherent 100 gig. If we look at the higher modulation option, that's available sooner. It offers a good cost per bit reduction and the best spectral efficiency, but the reach is going to be somewhat limited, particularly if we have a network with 10 gig and DCMs. And then the 100 gig coherent with smaller pluggables. Really, the key advantage of that one is that it's going to give us good reach in a network with 10 gig and DCMs, which represents the majority of existing metros, as well as giving cost per bit improvement and better spectral efficiency than we're getting with 10 gig. So those are the three options. So they each have their strengths and weaknesses in terms of cost per bit, reach, compatibility with existing 10 gig metros, and spectral efficiency.
Nice layout of all the options and their trade-offs. And next, Robert's going to dig a little deeper into the CFP2 ACO that Ron mentioned earlier.
Yeah, so what we've done here is really put all the optical functionality that I showed you earlier into one pluggable module, right? And that's the CFP2 ACO for analog coherent optics. The DSP in this design resides on the line card, and that's really the best solution from a technical perspective, and it allows to really run the DSP in different options, different modulation formats. What we're hearing from our customers is that having all the optics in one module is really a big advantage in terms of just multi-sourcing, and if you think of it as one component, you're basically replacing what were 4 optical components with one, but then also you have a handful of critical ICs that are all inside this module that's basically calibrated over temperature, has all the control electronics, bias circuitry, fiber routing all inside. And it really enables high-density line cards, So it's not just the 100 gig module. It's essentially a combo of what Paul just talked about, because it has a linear interface, and so you can run it at 200 or even 250 gig with 16 QAM or other modulation formats. So if you think of it in terms of density, that really gives you a lot higher density than, say, a traditional MSA module or even a CFP at 100 gig. Basically, you can have 4 or 5x the density of other 100 gig approaches. So that's basically our approach for the metro, and we'll talk a little more about it in the following slides.
Great, thanks, Robert. And Ron, you talked about this continuum, and most of the industry has expected all of these different lanes and points along this traversal to change at the same time. How do you think we're going to scale?
Yeah, I think over the next couple of years, Michael, we'll see some pretty significant changes. Like for instance, and maybe they're just from an innovation pace perspective, they're keeping pace with what we've seen over the past few years. But we'll see 25 gig lanes go to 56 gig lanes with the introduction of PAM4 at the electrical level. We'll also see that same technology enable higher speed optics at the optical level to allow for the pluggables to go from a QSFP 100 gig today to a QSFP 56, which will support 200 gig. At the same time, we'll see the coherent technology introduce some new modes which allow us to drive even faster speeds. So today there's lots of situations where even at the fastest DSP speed today at 250 gigabits, we still don't have we still have more margin, more capability in the optics than we need. The application is much shorter than that typically, And so driving the optics to speeds like 500 gig will more appropriately size the capacity to the application, and therefore increase the denominator and decrease the total cost per bit feeding into the ROADM. And what we'll talk about in a little while is an overarching technology to all of this called flexible Ethernet, which allows for each of these steps to be different. You know, they're kind of divisible by 25 in general, but you could have different number of lanes at the electrical level versus the optical level versus the DWDM level, and still from an end-to-end perspective, from a router talking to a router or a switch talking to a switch, have a connection that looks like one big fat pipe. And what happens in the middle really can be grown and have a life cycle all to itself, so that when the latest coherent technology comes out, we don't have to wait for other technologies to catch up. We can go ahead and move forward with that very quickly and leverage that for its value at that spot in the network.
Cool. Good stuff, Ron. So now we're going to move on to service provider deployment applications, and I'm going to ask Paul to kick off here.
Okay, so before we can examine which option 100 gig has the best fit of the options I discussed previously, we need to identify some network scenarios in the metro. So the first scenario that I'd like to focus on is what I'll call the traditional metro, and this is what you see in the majority of communication service providers, be they incumbents, alternative fixed operators, or mobile operators. And this is typically somewhere between a ring and a mesh topology, dominated by 10 gig, relatively short spans with a few OLAs, if any. And really the distinguishing feature for this type of network is that the 100 gig has to coexist with 10 gig and with DCMs. So that's the first one, the kind of traditional ring mesh 10 gig metro. Then the second scenario is something we're starting to see in the either larger or more aggressive communication service providers, primarily in the larger metros with lots of data centers, in order to meet the kind of east-west requirements of data center interconnect primarily. And this is where you build a coherent overlay, so either a kind of separate overlay network that is coherent only, or it can be done with coherent only spans in a kind of mixed network, but having ROADM spans that are coherent only. So that's the second scenario, coherent overlay. And then the third scenario is point-to-point data center interconnect. And this is more often seen at internet content providers, carrier neutral providers, enterprise and government type of customers, as well as also in the communication service providers. And even though the topology could be ring-based or look more like a ring, from a DWDM perspective, it's really point-to-point without pass-through from one span to the next. And within this scenario, you see lots of sub-scenarios based on whether fiber is easily available and cost-effective or very expensive, dependent on the different bandwidth requirements and dependent on the different distance and reach requirements. So those are the three key scenarios. In terms of which of the technologies I discussed previously has a good fit, if we look at the traditional metro, probably the technology that's going to dominate there is going to smaller pluggables but keeping the coherent 100 gig, and this is for compatibility reasons. Yet at the same time offering cost reductions and spectral efficiency improvements. In this scenario, the higher modulation is probably going to have more of a niche role for some short high bandwidth routes, and the non-coherent for access. Just looking at the second scenario we discussed, which is coherent only overlay, probably the key technology for this segment is the higher modulation, going to 16 QAM to get the both cost per bit and spectral efficiency. Probably a secondary role for the smaller pluggable coherent 100 gig if there's requirements for longer reach and to leverage the kind of first cost of the smaller pluggable 100 gig. And then also maybe a niche role for non-coherent for single span and customer access. And then finally, the data center interconnect. Really here there are kind of two horses in this race. There's the higher modulation for spectral efficiency and reach, and the non-coherent for the lowest cost per bit. So really depending on the scenario and which is the priority, spectral efficiency or lowest cost per bit, and also depending on timing, there's a strong role for both of those technologies, and also maybe a more niche role for smaller pluggable coherent 100 gig, particularly where reach is an issue.
Okay, good. So
Michael?
one of the most important applications is data center interconnect. And I remember quite a few years ago, I visited the Amsterdam IX, the AMS-IX, and when I went there, I was expecting to see all of the great network equipment and essentially a data center as well. When I asked them to look at the equipment, they said, "Oh, well, there's 4 locations around Amsterdam. We're not all in one place." And aha! So even a single data center, big metros have multiples. I visited Equinix several years ago, and they have 4 or 5, I forgot how many, around the Bay Area here. And Google's in each one of them, and others, cloud providers are in each of those data centers as well. So the data centers then 3 or 4 or 5 or 6 around the metro have to speak to each other. So the cloud providers, cloud service providers need maximum bandwidth to treat each of those distributed data centers as a single data center. So now, Robert, talk to us about the role of the CFP2 ACO in that important DCI application.
Yeah, thanks, Michael. I mean, it's just amazing the efficiencies of scale and the amount of data that the mega scale data center guys are requiring, right? So, as you said, there are sort of the metropolitan areas where you have multiple data centers that really need to be interconnected via point-to-point links, tens of kilometers, say, or up to 80 kilometers, and that's one of the requirements. But there are also requirements where basically you do interconnect data centers over hundreds of kilometers, going through a traditional network, or really over the long haul or ultra long haul, even up to a few thousand kilometers. So this is what we refer to as DCI, or data center interconnect, and it's a few different requirements really that are put onto this segment. What we're seeing, the initial pull really for the CFP2 ACO is really primarily for this data center interconnect application. And what is interesting is that with the flexibility and the modulation format, you can really do different data rates for different reach. So, for example, you can do 100 gig QPSK and go let's say 3,000 kilometers, or you can decide that you only need to go 200 or 300 kilometers, and you're going to use a 16 QAM and do 250 gig. So you can do either say 800 gig with 8 CFP2s that have 100 gig per 1 RU, or you can do 2 terabits if you do 8 times 250 gig. So this flexibility with the linear interface and optimizing the data rate for a given reach is really what's driving a lot of the demand for these CFP2 ACOs for this application. Michael?
Great, thanks. And some of those data center interconnects are 10 kilometers or less, and others are 200 around the metro. So what are some of the prevailing topologies, Ron?
I think this is an interesting topic and something that I find a lot of confusion on. That today what I see is that almost all DWDM is point to point. It may be physically routed over a road of mesh network. It may be physically routed over just a point to point AWG system. But the thing that's interesting is the variation in distance. And we see lots and lots of bandwidth that's very short distance, like the one shown here across Manhattan, or even a link that's from Dallas to Chicago. And I think what the opportunity that exists is really to start to look at how to trade the distance that you have to go in the network for capacity. And I would say that the industry right now across the board has started to introduce some rough ways to do that. Things like supporting multiple modulations like BPSK, QPSK, 16 QAM in the same DSP. And this gives us a way to optimize around some very specific applications like really, really long haul or really short applications. But there's a lot of variability that's much shorter than this or between long haul and these metro distances that can be optimized for. And where we see this going is that we will continue to drive up the baud rate and also at the same time add more modulation options to the next generation of DSPs that give us the ability to have more granularity so that you can start to trade different capacity rates. So in this case, it's showing 200 gig at QPSK all the way through 600 gig at 64 QAM, and each of those will support varying levels of distance. There's even investment in technology that's going to take us beyond this, where we can get more granularity down to 25 gigabit increments so that we can really precisely remove all of the extra performance out of the network that's not required for a specific application. The key from my perspective to leveraging this is at the upper layer supporting this flexible Ethernet that we talked about earlier. And one of the capabilities or some of the promises of this technology are that we can start to look at different rates, maximizing the amount of capacity you can get in each wavelength of the DWDM system across whatever distance is required. It may be 10 kilometers, it may be 1,000 kilometers, but maximize how much capacity you get per wavelength, and then just apply however many wavelengths are required to support the Ethernet interface that's required between the two routers. And by doing that, we solve some interesting problems in the network. Today, this is typically done through the use of lag groups. And we see oftentimes that the network is built in such a way that the router has an interface, it plugs into a transponder that transponds it to an interface of the same capacity on fiber. And what we want to do is be able to have the router have as much capacity as it needs. Let's say it's a 1.5 terabits. If the best technology we can get across that distance is 100 gig per wavelength, then it's going to take 15 carriers to do it. But if the best technology is 500 gigabits that we can get across that, it'll only take 3 carriers to do it. And the carriers are very proportional to the cost that it takes to implement that network. So you could see that 3 divided by 1.5 terabits is a much lower cost per bit than 10 divided by 1.5 terabits.
Nice. So essentially what we're doing as we get faster movement of data through a network or over a wave, it's good to break up the data into larger chunks, not Ethernet frames, But here we have 25 gigs at a time to be now the new atomic unit, or a potential new atomic unit of how you move the data. And that makes it flexible through each station along the way, along the pathway. Do you see that as kind of like a cell of Ethernet, or just a big frame, uber frame of Ethernet?
You can think of it like a cell. I mean, I think it's, you could really think of it as an in by 25 gig contiguous pipe. So, if it's 1.5 terabits, it's 15 times 4 times that capacity of 25 gig lanes that make up that 1.5 terabits. But to the router, it looks at it as one interface instead of as many discrete interfaces that have to use a hashing algorithm to apply the bandwidth to those discrete interfaces.
Great. Okay. So lots of questions coming in. Be sure to submit yours. We have a lot of good questions coming in. It'll be fun. So now we're going to take a few minutes to go through sponsor approaches, and Paul's up first.
Okay, so what's the coherent approach to 100 gig in the metro? Well, today we have single slot 100 gig with coherent CFPs, as well as very high density 10 gig with 8 10 gig transponders based on SFP plus on a single module in our metro products. In the short to medium term, we see a strong role for each of the approaches that I discussed previously. So 8QAM and 16QAM based on our Corian CloudWave technology, going to smaller pluggables with coherent 100 gig based on CFP2 ACO, as well as non-coherent 100 gig based on PAM4 and DNT. So we see a strong role for each of those technologies and plan to support them in our metro product lines in the short to medium term. A great example of this is yesterday we announced our Groove G30 data center interconnect platform, which delivers a game-changing 3.2 terabits in one rack unit, and we're doing that with has 8 200 gig DWDM interfaces based on 16QAM and CFP2 ACO pluggables. So that's an example of how we're bringing both the smaller pluggables as well as the higher modulation to the metro to deliver significant gains in terms of cost per bit, footprint, and power consumption. Thanks.
New product yesterday, huh? Great. And another competitor for the DCI space, for the metro space. Okay, great. Robert, what's the Oclaro approach?
Yes, I wanted to just spend a minute talking about what's really enabling us to get into the CFP2 ACO form factor. It's really all around about photonic integration in indium phosphide. What we're doing to really shrink the laser and modulator is that we have an indium phosphide-based Mach-Zehnder modulator, and in fact we're putting SOAs or semiconductor optical amplifier onto that modulator chip to boost the output power, because as you go to these advanced modulation formats, really you incur an additional penalty, and to compensate for that, you really have to have significant output power, and to do that we have SOAs not just on the laser but also on the modulator. Similarly, we have shrunk the receiver, so all of that enables us to get into this small, compact CFP2 ACO. We see it really moving towards higher baud rate, as Ron talked about also. We think that within the CFP2 ACO, we can get to 64 gigabaud, so that you could do 400 gig or 500 gig per CFP2, which would get us to 4 terabits per rack unit. And then also we have done some work on parallel integration, where we have not just one laser but 4 lasers and 4 modulators on the same chip, which I'm showing at the bottom. So what we could do is basically go more parallel and then get to 1 or 2 terabit components through that step. The other thing I wanted to briefly touch on is these point-to-point links that Paul talked about. And the idea here is really that you go somewhat back in time away from coherent. I mean, obviously, coherent has great advantages in terms of OSNR performance and chromatic dispersion. Here, you're looking at an alternative where you basically go into the QSFP28 form factor, which is obviously what's being deployed inside the switches in the data centers now. And you do a single wavelength DWDM QSFP28 that you then multiplex via an AWG and go through a dispersion compensated link, amplified and dispersion compensated. And that way you can really do point-to-point links for tens of kilometers, maybe up to 80 kilometers, using either PAM4 or DMT. But for that to be really feasible, you need the next gen DSPs, really in 60 nanometer technology. So that's really something that's a little bit further out, but it really enables you to do high capacity links, 4 or 10 terabit per fiber point to point for some of those data center interconnects within a city or metropolitan area. So that's quite exciting, and it's really based again on our indium phosphide high speed technology. So we're quite excited about that as well, not just the CFP2, but what's next basically. Back to you, Michael.
Yeah, thanks, Robert. And Ron, Cisco's approach.
I just wanted to highlight a couple of things. We've invested now in our 6th generation of ROADM, and I would say that we're finally now in a phase where ROADM is really living up to the R, that it's completely reconfigurable. These things in combination are very compact. They have a tight integration of amplification, optical service channel, the channel monitoring, the WSS, but more importantly, they introduce flex spectrum and colorless, directionless, contentionless technology to this space. So now we can really build the infrastructure in such a way that it's completely flexible. We can later come back in with much higher modulation, much higher baud rates, and squeeze those channels very closely together to scale many and most applications, above 20 terabits of capacity in fiber. At the same time, we've really focused a lot on the operation, and this will be a common thing you see between this and our DCI box. We focused a lot on the operationalization of the platform. In this case, we're looking at every fiber connection and verifying that every fiber connection is valid continually in the product. It's something we call connection verification. We've also introduced an optical time domain reflectometer, which gives us the capability to scope both the transmit and receive fibers in every direction of the node to really narrow down any fault that occurs and be able to point resources at the problem very, very quickly and solve those problems very quickly. We also introduced last week a new product for the DCI space, which we call NCS 1000, and this product is a pizza box. It has 2 terabits of capacity on the client side via 20 QSFP28s, and it has 2 terabits of capacity on the trunk side. And the interesting thing about the trunk side is it enables a higher baud rate 16 QAM that allows us to get 250 gigabits into a single carrier. So in 8 carriers, we're able to get 2 terabits of capacity. And maybe even more importantly than the density or the capability of this platform is the operational capabilities. We really focused on taking our leading XR60 software and enabling some very important features like model-based provisioning and telemetry with native Yang support on the platform. With that, I'll turn it back to you, Michael.
Yeah, thanks, Ron. So lots of exciting new technologies in the metro. So conclusions, let me briefly go through these and we'll get to we have a lot of questions, but be sure to submit yours. So today we're talking about the metro 100G coherent evolution, which includes beyond 100G, it includes non-coherent. But basically, long haul is done, although not totally done, but basically next year we'll probably see saturation. A lot of deployments, but for the most part, few or single technologies. There's a lot of different traffic uses, IP, cloud, video, 4G, 5G, the Internet of Things, and what we've learned today, there's a lot of different technologies for Metro 100G use and use cases, the data center interconnect, telco, metro aggregation. There's multiple innovation areas. We heard 56 gig channels per channel, 400 gig pluggable optics, flexible Ethernet, and 56 gig units from router through DWDM transport. And each innovation area can proceed at its own pace. We don't need to have all the innovation areas proceed at once. Near-term options, we heard about non-coherent for the lowest cost and shorter distances, and the new coherent pluggables for higher densities, especially data center interconnect. Higher order modulation formats for higher capacities, certainly. And on the component side, we heard a lot about CFP2 ACO. It's a next-gen coherent interface for metro, for long haul, for data center interconnect. And the path to 400 gig per CFP2 ACO we heard about. Potential 1 terabit to 2 terabit modules and components. So that's our wrap up. So thank you for joining us. And now we'll get to your questions. We have a lot of good questions. And so let me, okay, lots of questions. So let's take this first one from an operator. Can we expect PAM4 and DMT on CFP4 or SFP28 form factor?
Yeah,
Robert,
I can answer that. Yeah, I mean, as we said, I mean, we believe we can get into a QSFP28 form factor. Obviously, power dissipation is a bit of a challenge, but CFP4 doesn't really make a lot of sense because it's not that interface that's deployed inside the data center. So I don't think you're going to see that. You're going to see QSFP28, and you're going to see it once it can hit sort of the 3.5 or 4 watt power requirement.
Any other comments, Ron or Paul? If not, we'll move on to the next question. So
yeah, I think it's going to be primarily QSFP28. I think to remember I saw one component vendor talk about CFP4. So there may be some variation in the market, but it certainly seems that QSFP28 looks like the most dominant form factor for that modulation.
Okay.
And maybe I should add. So sorry, maybe I wanted to just add one quick one. I mean, so people have talked about disaggregating the DSP. So there could be something like an analog SFP28 concept as well. So if you're interested, feel free to reach out to me separately.
Okay, good. So here's another question. Do you expect the CFP4 to support coherent modules?
Yeah, I think that's for me as well. Yeah. Okay, you go, Ron.
No, go ahead, Robert. I'll talk after you.
Yeah, I was gonna say, so that's certainly something that's on the roadmap, but at the same time, if you look at the sort of the development on the CFP2, driving it to higher baud rate, higher order modulation formats, and compensating for some of the losses we are, SOAs, we really see the CFP2 as the play for those higher density requirements. CFP4 is probably going to be more limited to sort of lower end applications, where we're not really pushing the envelope as much. But I think it's going to happen eventually, but more for the lower end, 100 gig or so.
Great, thank you. And anybody else? Sorry, go ahead. Ron?
Yeah, no, I was just going to comment that today the ecosystem for this technology is it's pretty critical for us to move forward and get that established in a meaningful way. And there's a number of different techniques and technologies like indium phosphide, silicon photonics, silicon optical amplifiers, EDFAs that are used to overcome some of the inherent losses of those technologies. And so, from my perspective, I think CFP2 will be around for some time. We'll see a transition from 250 gig today to above 500 gig, but it'll probably be here for at least this generation, the next generation, and then we'll see things become smaller, like in a CFP4 form factor, or maybe even 2 carriers inside of a single CFP2.
Great. Paul, any remarks? Are you okay?
No, I'm okay.
Okay. So, Ron, you talked about different types of traffic, bandwidth requirements. So here's a question from one of our audience members. If 4K video rolls out widely, what will that do to the metro bandwidth needs, or is that already planned for?
Yeah, I mean, I think in a lot of ways we're starting to already see that with a lot of 4K content on Netflix, a lot of 4K content on YouTube, and I think it's just a matter of how quickly some of the consumers start to or begin to leverage that more. And so it's even in Japan they're not only talking about 4K but talking about 8K video. So I think what's clear is that the appetite for better quality is high, and the consumption of some of these new technologies is very high, to a point where some of these networks are growing or doubling in 6-month intervals. And to think about having to scale a massive network in 6-month intervals from a doubling perspective is pretty mind-numbing. But I think it's an indication as to why the investment in this space is so high and why the pressure for the cost per bit is so intense in this market.
Paul or Robert, you want to comment? Are you okay?
Yeah, when I first read this question, if 4K rolls out widely, what are we going to do? And my first thought was I'm going to buy a new telly.
Okay, well, we'll move on then to the next question. So from one of our industry experts wondering about the future, when direct detect solutions become available, can they be supported in the existing CFP2 ACO sockets, or will the host hardware need an update?
Yeah, let me have a go at that one.
Yeah.
This is Paul. I can have a go at that one.
Okay, go.
Yeah, so I think there's a couple of factors. One is, are the direct detect going to be available in a CFP2 form factor? And I think the answer to that is no. It's most likely going to be QSFP28, and if it's anything else, it's probably going to be CFP4. So that's the first issue. The second issue is that with CFP2 cards that support CFP2 ACO, they have a DSP on the card typically, and so you wouldn't want to waste the card that has a DSP where you paid for the DSP and use it for a direct detect technology. So that would kind of defeat the object. So direct detect is going to be most likely a different card, both to get rid of the DSP and also to have the right form factor for the direct detect pluggables.
Great. Any other comments?
Yeah, let me add to that. I mean, just to be extremely clear, the CFP2 ACO is a different interface, right, to the board. So the interface between the DSP and the CFP2 analog is an analog interface. And so traditional CFP2s like LR4 or SR10 or SR4 won't work in those same plug holes.
Okay, great. One final question. We're close to our end time, and I'll ask Ron this. What is the status of FlexE in terms of chip development and industry standards?
Yeah, I mean, from a chip development perspective, I think we'll have to stay tuned. But I think from a standardization perspective, I think there's general support by a broad range of both of chip suppliers, of network element suppliers, and of network providers who want to see this technology move forward. And so, there's an awareness around FlexE for the intermediate pieces that we talked about earlier, and then there's certainly an implication to the network processors or the switching and routing chips that are being developed now.
Great. Well, thank you. And with that, we're going to close our Q&A period. I want to thank all of you for attending, and Joanne's going to wrap up here at the end. Be sure to see all of the available documentation, good content that's on the website. But Joanne, and thank you to our distinguished panelists.
Yep, and also thank you, Michael, for leading the discussion, and I'll just formally thank Ron from Cisco, Paul from Corient, and Robert from Oclaro, and all the teams behind the scenes, behind the speakers for the presentation today. Also, of course, thanks to you in the audience for joining and participating today. The archive version of this webinar is going to be available shortly. You'll be receiving a follow-up email with more information about access to the archive and how you can share it with colleagues. Also, you'll see a short survey pop up. We do ask you to respond back, give us your feedback on this topic and other topics you'd like to see produced in a webinar. We hope to have you join us again and watch for more invitations from the IHS Technology Group. And that is all for this session. Thanks again, everyone, and have a great day.